So, welcome to talking about Introduction to Polar Coordinates. So, this is really about having a different way to do graphing. And the way that we are used to graphing is on what's called a Cartesian plane. It has a few other names. It's called a coordinate plane. A rare name is it's also called a rectangular plane. And this is the idea. If I wanted to graph 4, 4, I'd go right 4 units, up 4 units. So I'm moving to the right 4 and then up 4. And here's our point 4, 4. This is great and works well a lot of time, but it's really inconvenient at times, or it's difficult at times if we're only going to be moving left or right or up and down. Some cases where only moving left, right, and up, down is not feasible, at least in real life, is when you travel somewhere. For example, flying. Planes don't take off, make a right-hand turn, fly straight, make a left-hand turn, fly straight, make another right-hand turn, fly straight. They're curving. They're moving up and down. And same with most driving. I mean, downtown Cincinnati, yes, is laid out on a grid, so it is left and right, up and down. But typically when you're driving in the suburbs or rural areas, the roads take gentle curves and not right-hand turns and left-hand turns. So there are different ways of graphing points. And so one of the ways that we could graph points on a coordinate plane is to measure an angle and then move a certain distance where we are along that angle. So for example, I could say, hey, instead of moving right 4, up 4, let's say that I want to move 5.5 units at a 45-degree angle. So just like we did on the unit circle, if I say here my positive x-axis is where I start at and I move counterclockwise, a 45-degree angle would look like this. And then I want to move 5.5 units along here. Well, that's going to be a little bit tougher for us to do because in the diagonal of that square isn't exactly 1 unit. It's about 1.4 units. So that's 1.4, 2.8, 4.2. So I'm going to be about here. And if you notice, that's at about the coordinates 4, 4 from when we were graphing like normal. This was just a different way of getting there. But if you notice, there was some difficulty there. It's not always easy for us to measure angles on a Cartesian plane. And even when we do measure angles, it's not easy to figure out how far we're moving along that dotted line. So we switch to what's called a polar plane, where things are laid out around the origin. So here's our origin, which we're used to calling 0, 0. In a polar plane, we call that the pole because what we're imagining is that there's a string that we pull tight and swing around the pole to a specific angle. So if I were saying I wanted to do on this one, hey, we're going 45-degree angle, so I would start here as we're used to. I would move to a 45-degree angle. And each concentric circle here is 1 unit. So there's 1, 2, 3, 4, 5. 5.5 would be right about here. So this is set up in a way where it's easy for us to count units along any angle, and it's also easy for us to measure angles on because so many angles are previously marked. So if you notice, this is built off of the unit circle. We just say, hey, what if we have circles whose radius is not 1, like a radius of 2, a radius of 3, a radius of 4. So we're used to working at this and moving from the positive x-axis counterclockwise around. So another example of this is if I wanted to go 2 units at an angle of 210 degrees, well, starting here, I would go around to the 210 degrees and move out 1, 2 units. And there's our point. So when we're doing this here, what's happening is because we're on our polar plane, we are using polar coordinates. And polar coordinates are going to get written r comma theta, where r is the distance that we're moving, which we could also call a radius. and theta is the angle that we move at. So the point we plotted above where we went 2 units at an angle of 210 degrees in polar coordinates would be written as 2, 210 degrees.